Today we have a pleasure to host Osman. Osman is the 2021 Alvarez Postdoc Fellow at Lawrence Berkeley National Lab, where he is a member of the Scalable Solvers group. He received his PhD in applied mathematics from University of Colorado, Boulder, if I'm correct, where he was advised by Stephen Becker. His research is revolving around randomized algorithms, tensor networks methods, optimization, and quantum computing. Okay, Osman, stage is yours.
Thank you so much, Beheshten. Thanks for this invitation to give this talk. So let me go ahead and share my slides. Okay, is this looking good? Okay. So I will talk today about some work that I've been working on for a while, which is on sampling-based decomposition algorithms for arbitrary tensor networks. So just to kind of set the stage and give a little bit of a background for the types of problems we're considering, we're focusing on decomposition of very large tensors. So this can pose certain problems that don't come up for smaller data sets. So just to give an example, this is a data set that was collected at UCSD by the Center for Applied Internet Data Analysis. And what they did is during 2019 and 2020, they collected over 40 trillion unique packets, or they collected information about these packets. And this data can be represented as a three-way tensor. So an entry on position S, D, T represents information about a packet that was sent from source S to destination D at time T. In one of our papers, we look at just a small subset of this data, and I actually don't know what proportion of the total data set we're looking at here, but it's a very small portion, and it's still consists of almost 7 billion non-zeros, and the size is 3.6 million by 11 million by 54,000. So this is already very large and difficult to handle. And if we were to look at the full data set, it turns out it's stored on magnetic tape. And this means it's expensive to look at it in some sense because you have to, there can be various difficulties. I think around the time we were working on this paper, there were fires going on nearby in California, so the air quality was bad. So we weren't able to even access the data on the tape because it could harm the tape or something along these lines. So this is kind of the sorts of problems we're thinking about where the data set is very large. So here's some background material I'm sure all of you probably are very familiar with, so I'll go through it fairly quickly. I will use this graphical tensor network notation throughout the talk to make things a little bit more clear. So the way this notation works is a circle with no legs is a scalar, circle with one leg is a vector, two legs it means it's a matrix, and four legs, for example, means it's a four-way tensor. And this notation can also be used for representing various contractions between tensors. For example, if you connect the legs like this on a matrix, it means trace. If you do something like this, it represents matrix vector product. This represents matrix product, and this here represents a Tucker decomposition of a three-way tensor. And here on the right-hand side, you have the corresponding mathematical notation. So you can see this makes things a lot easier because you can avoid all of these indices. And here are some other examples of what these what common decompositions may look like in this notation. And this is the CP decomposition here, and this represents a diagonal tensor. This tensor in the middle here, and this is a tensor ring. So these two I'll talk a little bit more about in this talk. So that's why I'm choosing to highlight them here. When it comes to computing a tensor decomposition, and in particular fitting a tensor decomposition of some kind to a data tensor, this is known to be difficult since it's a non-convex optimization problem. And unlike the matrix factorizations, where for a lot of them we have very nice algorithms that can run in polynomial time and give you very nice results, for tensors, the story is more complicated. So there's some different ways you could do this. And the most popular one is to use some kind of alternating least squares. Other options would be to use something like gradient descent, stochastic gradient descent, these kind of techniques, and that's fine as well, that works. But ALS or alternating least squares is one that has turned out to be very popular in practice. When it comes to alternating least squares, what we do is instead of solving this problem up here, which is trying to optimize all of these cores at the same time, in alternating least squares, we do something less ambitious, which is to optimize a single core or factor matrix in this case for the CP decomposition at a time. So first we only optimize this red tensor and we keep everything else fixed. So the 3 blue tensors are fixed here. Then we go on to optimize the next one and keep the other 3 fixed. And then we kind of iterate through in this fashion. And then we start over and we do this over and over again until some kind of convergence that we're satisfied with has been reached. And the reason this is popular is that each of these subproblems where we're only updating a single tensor at a time turns out to be a linear least square problem. And this is now in principle very easy to solve because we've boiled it down to matrix algorithms. So we can solve this using backslash in MATLAB or linear solve in Python. And this kind of basic algorithm with a few added things like convergence, checking, termination criteria, this sort of stuff. But this basic algorithm that I've described here is basically how alternating least squares is implemented in packages like Tensor Toolbox and Tensorly and other places. So this algorithm, it works well. And a nice thing about this kind of idea is that it can be used not just for CP decomposition, which is the example I showed on the last slide, but it works in fact for any tensor, any tensor network. So you could go through the same kind of idea and isolate one tensor that you want to solve for, and then you restructure everything else into a design matrix and you solve via least squares. And to kind of understand how this works, and throughout this talk, I've tried to keep sort of a graphical notation instead of math, so we'll see how that works, but I hope it makes sense. And here on this slide, I just want to explain in graphics how this becomes a linear problem. So here is again one of these tensors that we're updating. And if we do a little bit of algebra, or in this case, we just sort of bend the graphical components here and the legs, we can turn it into a linear problem. So essentially what we do here is we gather 3 of the 4 modes on one side and them on one mode corresponding to the red tensor on the other side. So this gives us a matrix here. And then we do a similar orientation of the tensor itself that we're or the tensor decomposition itself. So we have 3 legs pointing left, representing rows, 1 leg pointing right, representing columns, and that's how we get our system. And so this hasn't really changed. This only corresponds to permuting and reshaping the tensors. So yeah, so this is what I mentioned. These are matrix rows. These are matrix columns. And this here is now the design matrix. So if we were to make a cut here, this is the design matrix, and the red tensor is the thing we're trying to solve for. And yeah, so this is what I mentioned earlier. There's other options available like gradient descent, but this kind of alternating approach is very popular. So this kind of algorithm works well in practice, and like I mentioned earlier, with just some minor bells and whistles added, this is how it's implemented in a lot of toolboxes. But the problem we run into is when we're considering these really large tensors that we're thinking about. So in particular, if we have a tensor which is n ways, so meaning there's n indices on the tensor, and suppose each dimension is capital I, so each index goes from 1 up to capital I, so the tensor is like this, I by I by I by I, then the design matrix, so that's what I call them, has up to I to the n minus 1 rows. So here we have this exponential dependence on the number of modes of the tensor. And this means that the cost of solving the linear least square problem using a standard direct method scales with this number. So it scales like I to the n. And then, and this is in some ways, if you want to do sort of an exact algorithm, this is inevitable because this is also how many roughly, if you look at all the entries in the tensor, it has to I to the n entries. So in some sense, it's inevitable if you want to take the entire tensor into account when you do a decomposition. But maybe there are ways to improve this when we do these kind of iterative methods and at least improve the cost per iteration of an alternating least square scheme. So this is kind of the goal of the things we've been working on. And to do this, we use a popular tool from the field of randomized numerical linear algebra, which is to sample equations randomly. So if we have a large overdetermined least square problem like this, which is the case in CP decomposition and Tucker and many other tensor decompositions. So if we have a problem like this, the idea is to quite simply sample some of the equations, some of the rows of this system, and then end up with a smaller system. So here, this S matrix in red here, it signifies the sampling operator that does this operation. So it's very sparse. And in addition to sampling some of the rows, it also rescales them in a certain way to make sure things are scaled appropriately. So this is sort of a very nice, attractive idea. It makes the system smaller and cheaper to solve. So the question now is, how do we do this sampling? Can we do it just uniformly at random? Does it matter how we do it? And the answer is, if we want to have theoretical guarantees, it does matter how we do it. And a good way to do this sampling is to sample according to something called the leverage score distribution. And this distribution is defined as follows. So first, let's suppose M is our design matrix. And suppose we have a thin SVD of M, meaning we discard any singular values that are 0 and only keep the ones that are positive. So then we have a distribution or a decomposition that looks like this. And we're going to, in particular, focus here and use this U matrix. So this contains the basis for the range of the design matrix. Then the distribution we would like to use when drawing rows is defined in this way. So we draw a row I in this original design matrix with a probability which is proportional to the squared Euclidean norm of the ith row of this U matrix. So in some sense, this captures the importance of the row in the original design matrix. And this rank M here is just, it turns out to be the correct rescaling factor to ensure that this all adds up to 1. So the important part here is that it's proportional to the Euclidean norm squared of the ith row of the U matrix. And if we do this sampling with replacement and IID in particular, then according to this distribution, we can get some nice, strong guarantees for the performance. So here I will just briefly say a little bit about what the performance guarantees are. So again, we have this thin SVD for the design matrix. And this is again our distribution, so it's proportional to the row norm squared of U. If we then sample these rows, again, IID according to this distribution, then with some probability of 1 minus delta, so this here the delta represents the probability of failing, basically. So we would like this to be small, say 1%. With 99% chance, if we solve this sampled problem and get a solution A tilde, if we now plug that into the original least square problem, then the objective value of doing so is no more than 1 plus a factor epsilon worse than the best we could have done if we solved the unsampled least square problem. So there are two things here that are floating around. One is this delta, the other one, and I said that can be something small like 0.01, and this epsilon, which is also something small, say it's a 1 or 0.1 or something like that. And depending on how you choose delta and epsilon, that will impact the number of samples you need to draw in order to get these kind of guarantees. So I'm sort of sweeping some things under the rug here. So this can be made more precise, but I just want to sort of highlight the important bits here. And in particular, if we treat delta and epsilon as some fixed constants, then it's sufficient to choose roughly almost linear in the number of columns of the matrix M. So I don't know if I said this anywhere, but R here is, or in fact, this is the rank of the matrix M. And if it's full rank, it's the same as the number of columns of M. But we need roughly R log R samples. Oh yeah, I say here what it is. So it's the rank of M. So this is quite good. This means we can sample it down to essentially a square matrix. So not quite, but almost. And this also comes back to what I mentioned earlier, which is this idea of, can we somehow solve these sub least square problems without touching all the elements of the tensor that we're decomposing? And with this kind of a sampling approach, since we only look at a subset of the entries of the tensor we're decomposing, it turns out we can actually get one of these input sublinear solvers, at least on a per iteration basis. So it's input sublinear in the number of entries in the tensor we're decomposing. So there's been quite a few papers recently that use this idea of sampling specifically for the purpose of tensor decomposition and in alternating least squares, the alternating least square setting. So I'm talking about these two papers today. And here's sort of a summary. So there were some early works that first considered the CP decomposition. Then I had an earlier paper that looked at tensor ring decomposition. And there's some more here that do CP and Tucker and tensor ring and so on. So these are all focused on specific kinds of decompositions. And many of these also do sampling according to leverage scores, but not according to the exact leverage score distributions. They sample to some kind of approximation of the distribution. So this paper here, which is kind of the last, or this is what I will talk about today, and kind of the title of the talk as well, is how we can do this not just for a specific decomposition, but for any tensor network decomposition. And in addition to that, it's also sampling according to the exact leverage scores. And then we have a row here at the bottom, which is doing even better, but specifically for the CP decomposition. So this is what Vivek, one of my collaborators, he will talk about this next week in the tensor network reading group. So he'll tell you how to make this really efficient and how to do a real good high performance implementation. Okay, so, okay, there's a question, yeah.
Yes, I have a question about the basics before going to the your main paper. Here, if you take SVD of this large matrix each time, isn't it itself computationally expensive?
That's true, and that's a very good point. So that's actually what this next slide is about. So if we were to do what I've said so far, we have this huge matrix that we want to that we have as our design matrix. So that's what we called M earlier. And if we were to do an SVD on that matrix and then sample, just doing that SVD itself is as expensive as solving the least square problem. And that's the cost we're trying to avoid. So in fact, we have to somehow avoid that cost. And that's because, so one way to solve a least square problem is to first do this SVD, and then once you have the SVD, it's relatively cheap to do the actual solving of the system. But our goal is to avoid that cost. So in particular, the first thing we want to do is we want to avoid computing this U, because that's as expensive as solving the linear system. So in terms of the numbers I said earlier, this would cost something like I to the n-1th power times r squared for a rank R CP decomposition. So then we would immediately incur this cost that we wanted to avoid. And a smaller problem, but still something we may want to avoid, is even storing this probability distribution. So if we have a tensor where, or a design matrix which is very, very large, even storing the probability distribution and having it in memory and sampling from it may be too expensive. So in particular, it would need this exponential number of numbers to store. So our hope is to avoid both in the work we do. So before going into how we do it, I want to give a little bit of background and say how some earlier works did it, so we can put it into context. So let's see, here's again the problem that we have, and these papers that I will mention, so it's in particular this by Cheng et al. And one by Larson and Kolda, they both consider the CP decomposition. So in this case, the least square problem looks like this. We have our design matrix, and this is again what a thin SVD would look like. So what they do in order to avoid this cost of actually computing this big decomposition is the following. So the first step they do is they look at each of the factor matrices that appear in this design matrix. Then instead of using them to form this big matrix and then computing leverage scores for that big matrix, what they do is they instead compute leverage scores for each of these independently. And these are, of course, a lot smaller than this big matrix would be. So this is very cheap to do. So they can afford to do an SVD and do all of these computations to actually form these separate, in this case, 3 probability distributions. Then once you've done that, the next step is to sample independently from each distribution and index. And then the last step is to convert these into a sort of a big index or big matrix index. So and that then would, and this is kind of by just matching whatever this triple of numbers corresponds to in this big matrix. So they do this, and then they have a sample. After doing one sample, you can go back and do many by simply redrawing another triple, computing the next index, and so on. So this is how they compute their samples. And the nice thing about this is that it's very cheap to compute these smaller distributions, so that's affordable to do. And second of all, it's very, very fast, the sampling. And the reason is that you can just sort of draw this first index, draw the second one, draw the third one, and they can do this independently and in parallel, for example. The downside is that this is not leading to a sample. This kind of sampling approach does not draw from the exact leverage score distribution, but rather it draws from an approximation to the distribution. And this fact means that the sampling complexity, or the number of samples that you need in order to get guarantees, in fact scales like R to the n. So on an earlier slide, I said it's if you sample according to the exact leverage score distribution, it's enough with R log R or almost R samples. But here you can see this is a much bigger number because this is now R to the n rather than R log R. So this is kind of the downside. So before going into how we do this, I want to sort of highlight for a few different decompositions what the design matrices would look like if we were to solve them using alternating least squares. And the goal here is a little bit to kind of highlight how this tensor network structure translates to having a structured design matrix. So here we first have the CP decomposition. If we're fitting this tensor here, then this is what the design matrix looks like. So this is the example we've already seen. Here's tensor ring. If we take this one out and try to optimize for this tensor, then we get, excuse me, then we get a design matrix which looks like this. And here I try to find something exotic. So I find what I call the tiger decomposition, and it's from a paper by Lee and Sun. And what they do in this paper is they try to find decompositions that work well to decompose specific things. So they essentially both decompose and find the decomposition format itself. And they use this to decompose a picture of a tiger. So they find that this kind of tensor network structure works particularly well for that particular picture. So this is a lot more complicated, but if we were to remove a tensor here and try to optimize for it in an alternating least square scheme, we would get a design matrix that looks like this. So the point is to kind of show that conceptually it's very easy to go from, or to find these design matrices. And it's of course another story to kind of get this implemented nice in code, but this is what it would look like. So the red legs here are columns and then the green ones are rows. So essentially this could be done, the approach I'll talk about could be done for any of these. And just for the sake of illustration, I'm just going to suppose that this is what the design matrix tensor network structure is. So instead of this, you could use any of these other ones for CP tensoring, Tiger tensor, or any of your other tensor networks that you work with. But suppose this is what our M looks like. So here are rows and here are columns. Okay, so now we're going to go back and think about how we can solve these problems that I mentioned earlier while still sampling according to the exact leverage score distribution. Are there any additional questions so far? Let's see here. Nothing in the chat.
Just a clarification question. So there is no assumption on the tensor network structure here.
That's true. So that's also a very good question. And I actually have a little asterisk down here, which says essentially that this works for any tensor network structure, but some of the claims that I make down here about things essentially making sense from an efficiency standpoint, you could come up with a tensor network that kind of breaks this. But it will work for, I don't think I've been able to think of a single tensor network that people actually use where this doesn't work, or it works for all of them, but the question is if it ends up being faster or not. So I think that's the that's a sort of a caveat. So this is again the leverage score distribution. So it's again, the idea is we want to have a probability of sampling row I, which is proportional to the norm squared of the ith row of this U matrix in the thin SVD. So the thing that we can use here is the following formula, and this is, in fact, this is fairly easy to double check. We could just sort of plug in the SVD in place of M and just do this computation, and it turns out that this here is equal to this thing. So this is the formula that we will use to as a basis for our method. And first, we're going to focus on this red part here, and in particular this M transpose M. So this is now a gram matrix, and one of the nice things about tensor networks is that if you have matrices in tensor network structure, you can compute the gram matrix very efficiently by simply contracting the tensor network. So this is the example we had here, or that I took on the last page. So we're assuming M looks like this. So computing this tensor network, we can do by doing tensor contraction. So we avoid forming M here. So we get our matrix M transpose M. And this is where the caveats come in. So this can be done efficiently, and this is kind of the asterisk, via tensor decomposition. And this is true for reasonable tensor networks. And it's not hard to come up with a tensor where it doesn't make sense. You could basically, if you have, for example, if you had a lot of columns on your tensor, more columns than rows, perhaps it wouldn't work. Or if you made it so that it's extremely expensive to contract. But I can't think of an example from the top of my head. But the idea, and for the CP decomposition, we have this nice property of the Cattari-Rao product that it just turns out into a pointwise product of smaller gram matrices and things. So for all of those decompositions, this is indeed very efficient to do, and there's nice formulas for doing it. So once this is done, we can go ahead and compute the gram matrix, or sorry, the pseudo inverse of this gram matrix, and this is also affordable to do. And this is kind of, again, this caveat where you could make it so that it's not affordable if you come up with a really bad tensor network. But if we take the example of CP, for example, then this M transpose M would be R by R, where R is the rank. So it would be R cubed to do this this pseudo inverse. So that's, I think, fair to consider affordable for typical cases, especially when you're doing, it doesn't even have to be low rank decomposition, but as long as it's not a really bad tensor network. So that's the first step. Oh, let me go back actually. So that's kind of getting this thing computed. And then after this, the idea is to sample indices in sequence in order to get a big index. So if you recall from the earlier slide, I was talking about how Cheng et al. And Larson and Kolda did this sampling, and they sampled from each of these subtensors. So that was in the case of the CP decomposition, but the same idea applies here. So they were sampling these three indices independently from each other from separate distributions. So essentially, when viewed as random variables, they were independent random variables. So what we do here is to, instead of sampling them, and the reason they then get a higher sampling complexity is because the true leverage score distribution, or under the true leverage score distributions, these samples or these random variables aren't independent. So our sampling strategy to kind of address this is to draw these separately, but conditionally on each other. So what this means is we first sample this first index, I1, then in order to make sure we stick to the true leverage score distribution, we draw the next index conditionally on the realization of this first one. And then we sample the third one conditionally on the realization of the two previous ones, and so on. And this can kind of be extended for cases where you have more indices as well. So this is kind of the key to how we can avoid sampling from all the rows of the matrix while still sticking to the true leverage score distribution. So that's kind of the idea, and here's a little bit more on how this works out in terms of using the tensor networks to do this efficiently. So this is just kind of restating the formula from the earlier slide. This is the distribution we want to use. And this here is that pseudo-inversed gram matrix. So this is something that we've already computed. And that's now represented here as a tensor in the middle. And then computing this kind of product of M and the center matrix and M transpose, that can also be done. Or actually, we're not going to do that. We're not going to form this quantity. We're just going to represent it mathematically for now. And then if we have this and we want to sample the first, okay, there's a question from Beheshtet.
Yeah, I have a quick question. So this kind of sampling, the conditional, so the advantage is that so we are not independently just sample all the rows, right? So just it is more cost efficient, I think, this kind of sampling, if I'm correct.
So it's more expensive than Larson and Kolda sampling because you have to do some simply because you have to take previous indices into account. So it ends up being more expensive and in fact a little bit hard to implement. And that's why I leave talking about the experiments to Vivek, who for next week, who did a very nice implementation for doing this very efficiently. So at least if you say, I want to draw 100 samples, then their method is faster. But then if you want to get the theoretical performance guarantees, at least if you want to stick to the somewhat conservative theoretical estimates for how many samples you need, then their method would be more expensive. That's right, because they would have to draw, to get to those guarantees, they would have to draw a very large number of samples. So overall, our method is cheaper if you want to stick to or follow the sort of recommended number of samples that the theory gives. That's right. But for a fixed number of samples, theirs is faster.
Gotcha, thanks.
So, okay, so let's look at, like, if we want to sample this first index, the way we can do this, or if we were to just sort of write this out mathematically, we would just sort of add up or marginalize out these two other indices so that we're left with only one, and then sample according to this vector. So that's how we would do it if we were to do kind of a intro probability class approach. And it turns out, since we now have tensor networks, we can compute this distribution efficiently, or we can do this kind of summing out of these two other indices efficiently. And that's kind of graphically corresponds to adding up these links here between these nodes here. So we're left only with two legs corresponding to the I1 index. And that would give us a matrix B1. And then the probability distribution now lies on the diagonal of this matrix. And this is something kind of mostly for explaining the idea, but in practice, you could make this even more efficient by not computing all the off-diagonal elements of this B1. But the idea is this is essentially computing this probability can be done efficiently using contraction of tensors or of these tensor nodes here. So that's how we get that distribution. We sample from it, and then we have our I1 determined. Then the next step is to sample I2 conditionally on I1. So probability of I2 given I1 is what we want now. And the way to compute this is to stick in here the value for I1 that we actually drew in the last step. And then we sum over all the indices I3, and that's how to get that conditional distribution for I2 given I1. And once again, this can be done via tensor network contraction. So I've removed the leg here because this is now a specific number that we have. It's the we've removed all the slices except for the one corresponding to the I1 that we did draw. And then here are the legs we're interested in, and then we just link up this last set of legs here. And the probability distribution that we want, so the conditional probability distribution now lies on the diagonal of this B2 matrix. And once again, this is just for sort of to make it into a nice mathematical formulation, but in practice you wouldn't compute the off diagonal elements here, but only the diagonal elements. Another question?
Sorry, I'm not sure if I missed some parts, because here do you put a constraint that make sure you have the probability, it's a probability distribution, like you have non-negative values and they sum to 1? Because I didn't see if you put any constraint on the elements of the tensor.
That's a very good question, and those constraints are here, and they come from, so let's see, I'm going to go back a little bit. So let's see here. So I'm going to have to think here a little bit of myself. So this is a Graham matrix. So this is positive semi-definite. And then this matrix will also be positive semi-definite. So this will definitely be non-negative. Then let's see, now I'm trying to remember, we may need to do okay, let me think. We may need to do a rescaling, and I'm getting this confused because the two papers, in the first of the two papers I based this talk on, there was a rescaling factor due to, there was some additional randomization in the algorithm that made it not exact. So you may need to do a rescaling, but that can also be done efficiently. Okay, Guillaume?
Yeah, I wanted to jump in on that. Like it's like when you look your tensor network below, the last one that you have here, grayed out, it's like here you have a matrix and the diagonal is your distribution. And so it's easy to normalize this basically, right? I think this is what you do what you can do in practice. This is very easy. You just here you take the diagonal of this matrix, this is a vector, and you just normalize it. But this is very cheap because this is a small vector.
Yeah, that's a great point. And I think that's what we did in the first paper. And then the second one, I don't quite remember. I think yeah. But yeah, like Guillaume said, it can be done efficiently by just summing and dividing.
I see. Thanks.
Okay, so this is kind of getting the distribution, and then we sample our I2, and then we do a similar approach for the last index, I3, and we sample I3 as well. And then we can use this triple of numbers to get sort of a big matrix index. And then we can repeat this over and over again. And as you can see here, this is a little bit more complicated compared to Larson and Kolda's approach, where they draw these indices I1, I2, I3 from separate distributions. So, and this comes back to Bahesh's question. So if you were to decide I want to draw 1,000 samples for both methods, then Larson and Kolda's method will be faster because they have a much sort of simpler approach to do the sampling. Guillaume?
Actually, I was wondering, like in the case of Larson and Kolda, do they still get guarantee, even though they are not actually drawing from the leverage score distribution, right? Because they don't end up, but it still have some theoretical guarantee, but then even on the theoretical side, the bound is larger in terms of the number of samples.
Yeah, exactly. So they have guarantees, but the number of samples they need to draw to get to those guarantees is a lot higher.
Okay.
So, and this is where it gets complicated because the theory itself is very conservative. So you usually get away with a lot fewer samples. But on the other hand, if you say you decide you definitely want to stick to the theoretical guarantees, then their method ends up being more expensive because they need an exponential in the number of modes, number of samples.
Interesting. And maybe it's a little bit not tangential, but you were saying like this theory is mostly conservative, but does there exist some lower bound as well that are pushing in the other direction?
Yeah, and I think this was something I worked a little bit on trying to figure out examples, and I think I came up with an example for CP decomposition where it really was necessary to have all those samples for it to work. Where basically, if you miss a sample, a particularly important row in your sampling, you break the whole problem, and or you sort of impact it in a strong way.
I see. Yeah, thanks.
So here's, I'm almost, okay, it's good. I'm almost out of time, and I'm also toward the end of the talk here. So here, I just want to kind of say a little bit about how this impacts the computational complexity. So here we're looking at specifically if this approach is applied to the CP decomposition. And suppose we have a rank R CP decomposition. It's an n-way tensor redecomposing, and its size I by I by I. And we are doing this it here means number of iterations in ALS. So straight away, it's important to note here that this it factor that comes up in all of these methods here will differ from method to method. In particular, say exact CP may require fewer iterations than a randomized method. So it's not 100% apples to apples here, but it still gives some indication of how they compare, at least on a per iteration basis, these methods. So here are, at the top is just regular CP ALS without any randomization. And you can see here that we have this on per iteration cost has this I to the n factor. So both this factor I as well as this power of n appearing here. Then in the Cheng et al. And Larson and Kolda papers, they improve this to something which is now, first of all, R in the base here. So that's typically smaller than I. And then, but then they still have this to the n factor here. So there's still an exponential dependence on n here on a per iteration basis. And then here we have the two papers that I discussed today. And in particular here, when we apply it to CP using this arbitrary tensor network method, the key difference here is that we're able to avoid this something to the n cost. So it's all polynomial now per iteration. And then next week, Vivek will talk about how this can be made even more efficient for the case of CP, and in particular, some of these, an I factor is turned into log I here, for example, using some clever techniques. So that's something to look forward to for next week. So this is the case of CP, and maybe I should also mention this, so what I've written down here, that in these complexities, I've sort of simplified some things. In particular, I'm ignoring log factors. I'm treating these accuracy epsilon parameter and this probability of failure as constants. So that's why otherwise they would appear in these expressions as well. And this pound it is the number of iterations. Here's a similar table, but for the tensor ring decomposition. So now the rank is given by a tuple in this case, and it's assumed all the ranks are the same, so they're all capital R. To get an n-way tensor, and each dimension is capital I. And again, there's some number of iterations. So here there's a large number of methods, and some of them are, so here I also included methods that are not ALS based. For example, here the standard ALS method for tensor ring has an I to the n factor. Then there's a variety of randomized methods here. So there's one here, for example, by Yuan et al., which improves. So K is, they use kind of a compression, a randomized sketch applied to each side of a tensor before doing the decomposition. So they're able to get it down to something smaller, which is K to the n, but there's still an n dependence, or something to the n dependence. Here's a method which instead uses SVD instead of ALS, and it too has this I to the n dependence. Now this is not iterative, so it's in fact quite fast. If you're able to afford to do the SVD in the first place, it can actually be quite fast. But the SVD based methods are also typically less accurate than the ALS based methods because you only sort of go through everything once. And so here's another one that uses randomized SVD, has an I to the n cost. And here's one of my older papers where we do an approach similar to Larson and Kolda, but on tensor ring. And we get this R to the n factor here. And here are these, the last two rows are using the ideas I've talked about today, and we're able to again avoid this something to the n cost in the per iteration cost. Okay, and this is my last slide. So some future directions that we're working on is to expand these ideas to other decompositions. In particular, working with Beheshta and Guillaume on doing this for tensor train. And we're also looking at doing high performance implementations of these methods. So especially things in, say, shared and distributed memory and being able to run this on GPUs and things like this. So in closing, I want to thank all the collaborators I've worked with on tensors recently. It's been really nice. And I want to thank you for listening to this talk, and happy to take any questions. And also feel free to email or reach out if you have any questions. Thank you so much.
Osman.
Yes, ma'am.
Any question?
I have one. Thank you very much, Osman. It was very interesting, the talk. So I have a quite general question. If I want to use like your method for an like arbitrary tensor network, like the contraction efficiency would be what I have to consider, because so for example, in the bounds that you said, I did not see anything related to that. So you assume that that part is efficient, I guess, or is that part what I have to consider? That's my main question.
Yeah, that's a very good point. And the reason I didn't give any complexities is because it will depend on what kind of decomposition it is. So for CP, so here were the numbers for CP and tensor train, and then depending on what the other decomposition is, it will be something else. But for something like tensor train, tensor ring, what else is there? Hierarchical Tucker. For all of these, it should be very efficient to do these contractions, or at least a lot more efficient than if you were to form the full matrix and then do sampling or solve using that full matrix. So it will definitely be something like you would have to sit down and like go through to see what the complexity ends up being. And I think for if you were to do, say, a more complicated tensor network, I've seen in physics, for example, they have really big tensor networks that include a lot of tensors. If you were to do something that looked like that, I think it would become just the order in the finding a good order to do the contraction, or like an optimal in some sense, or I guess optimal in computational sense by itself, I think would become difficult. So then there's various offers for finding either optimal or sort of maybe not optimal, but still that work well, contraction orders for harder tensor networks. So I think that would need to be a part if you were to implement, and I've thought a little bit about implementing maybe in Tensorly a tensor network decomposer for arbitrary, where you give it a graph and for your tensor network, and then it fits that decomposition to the decomposition corresponding to that graph. So I think in such a decomposition routine, you would also need to like incorporate something like ncon, which is a package for finding a good contraction order.
I see. Yeah, thanks.
So,
Hopefully, I'm very curious. I think I will try out your algorithm to see.
yeah, and I would recommend looking, especially and Vivek will talk about this next week. So it turns out it's actually quite hard to implement, especially this that I talked about in the, well, I guess both papers do this. This kind of sequential sampling is actually can be difficult to implement and get it really fast. So Vivek did a really nice job of implementing in Python and C++ code that does this efficiently, and additionally doesn't just sample from it doesn't just form a vector and then put it into a sampler for a discrete distribution, but it uses this kind of binary tree idea to that's how you go from I to log I in the cost. So I would recommend looking at that code first, just to get the best performance. Let's see, where did the reference go? So okay, maybe I can, oops, sorry. Oh, okay, I didn't mean to do that. Let's see, I will share again here. Let's see, sorry, I'm just gonna give you the, okay, maybe I'll just do here. So it's this paper on the last row here, so from NeurIPS. I would recommend looking at that implementation first, just to get, and that's for CP specifically. And I think extending those ideas to other non-CP tensor decompositions, I think is an interesting thing to do. And yeah, we're working with Beheshti and Guillaume on doing this specifically for the tensor train.
Okay, thank you.
Yeah, the CP one is on his GitHub, Vivek's GitHub, so I can share the link with you personally offline.
Thank you very much.
Yeah.
Thanks so much, Osman. It was a great talk. Yeah.
I had a question, also quick question.
Oh, sorry, Guillaume. Oh, sorry.
No,
I'm sorry.
worries.
I'm so sorry,
I didn't
Guillaume.
jump by. I didn't raise my hand, but kind of far-fetched. I'm just thinking of that now, but and maybe not even on the tensor side, but this idea that you're using sampling in an iterative algorithm, is there any connection with like active learning somehow? Because as you update your model, you're updating the level score distribution. So it's like you're sampling from a distribution that has been informed by the progress that you've made. And maybe even more, or their work, maybe even more on matrix or more simple problem, but that when you use sampling in this context of an iterative algorithm to speed up like this inner computation, that make the link with active learning.
Yeah, I wonder. I'm a little bit unfamiliar with active learning, but yeah, it sounds like it could be potentially a connection there. That would be interesting to look at.
Yeah, I'm not that familiar either, but it sounds somehow, it's like you update your model, and now you're updating the distribution, you're sampling some kind of target function, and as I said, it was a bit far-fetched.
Yeah, no, but it sounds like there could be, yeah, it's an interesting connection, or yeah.
Anyway, thanks for the talk. That's very nice.
Yeah, thank you so much for inviting me.
Thanks, Osman.
Thanks for all the good questions.
Have a good day.
You too.
Yeah, so thank you
Bye.
everyone.
Bye-bye.
Have a good day.
Bye.
Bye-bye. Thanks
Bye-bye.
again, Osman.